today in classical mechanics we try to see some information, some main ideas about the concept of gravitation. What is gravitation, first of all? Gravity, as you know, is the weight of an object. Normally in physics 101, we call the weight of an object as gravity, its weight. This object has a mass m, let's say 100 grams, 0.1 kilogram, but it has a weight. When you leave it, it falls down because of the pull of the earth. And the force acting on it is mass times the gravitational acceleration, g. However, the details of this force go back to the 17th century, Isaac Newton, basically. First of all, let me say that there are basically four kinds of interaction, or in some classifications there are three different kinds of forces. A force is a kind of interaction, and I will not write them here, but the first two, strong force, weak force, or strong interaction, weak interaction, arise only in the nucleus of an atom. It is the force, sort of interaction between the nucleons, protons, neutrons, etc. So it is not observed even outside the nucleus of the atom, where the electrons take part. So the first two forces, two of the four or two of the three, occur only in the nucleus of an atom. And there are two more, which we can observe directly by our eyes. One is the electromagnetic force. In some classification it is added to the second of the previous two, weak force. Electromagnetic interaction between the charged objects, but it dates back to the maybe more than 1 century later than the gravitation, the foundations of gravitation. Because we talk about for gravitation, which is the weakest of these four in magnitude. Because the strong force and weak force are much stronger, however, the range is very limited. Those two forces, strong and weak, arise only in the nucleus of nuclei of the atoms. Electromagnetic interaction, which we can observe even here in this room, arises between charged objects, as you know from previous courses. Like charges repel each other, plus plus, minus minus repel each other. Unlike charges, if one is positive, the other is negative, according to some classification which we aren't interested in now. They try to attract each other. So this is the third type, and one of the two observable ones in the macroscopic sense, even by your eyes and hands. The last one, gravitation, that we will try to see today, is by far the weakest. If, for example, we give the magnitude of 1 to one of them, let's say the strong force, this is on the order of 10 to the minus 39, 38. So it is 1 billionth of the billionth of the billionth, and even further smaller, weaker than the others. However, since these two, strong and weak, do not occur, are not observed, measured in the macroscopic sense, and the third one, electromagnetic interaction, for example, is there any electromagnetic interaction between the Earth and the Moon? Is there any electromagnetic force of attraction or repulsion between the Sun and the Earth? Almost no force, no such force exists, because the net charge of the Earth seems to be 0. It can be considered a neutral object, because the number of positive charges and the number of negative charges almost are equal, so they cancel each other. There's no net resultant charge in the Earth as a whole. similarly for the moon or for other celestial bodies, for example. So the only interaction, although by far the weakest of these four types, is the gravitation that keeps the, for instance, solar system together. The solar system, whose details were found, were suggested and then proven by Kepler and some other people in the 17th century, for instance. At one of the foci, one focus of an ellipse, there is the sun, and the elliptical orbit. They are not exactly perfect ellipse, but sort of circular-like orbits. All the planets are revolving around the sun in the solar system, in the plane of the solar system, for instance. And this is the only force, only interaction that keeps this system still as a closed system. But of course, the first person, notably, is Sir Isaac Newton, who thought about this matter in 1660s. We talk about the 17th, mid-17th century. There wasn't even any electricity, any Ampere, any Maxwell or Coulomb or some Faraday, etc. Some people, some physicists, the pioneers who worked on basically electricity and magnetism. So in Newton's time, there was no such electrical counterpart. However, the main idea is quite similar. The electromagnetic behavior and the gravitational behavior are, as we see in the equations, are quite similar. For example, let me immediately write the formula first and then talk about the details. For example, if you compare the case of gravitation with electromagnetic interaction, let's say this is, for instance, gravitation, this is the electrical part. In the gravitational part, we will have some mass, another mass, let me call it M1, M2. The masses of these objects, let me consider just two objects in free space, for example, because it is quite difficult to observe such a small force here. Here means on the Earth, because there are much higher, larger forces that annihilate the effect of gravitational force. So it is quite difficult. However, in free space, there is no friction, for instance. So the force of attraction, because gravitation is always attractive, unlike the electrical case where, as I said before, like charges repel, unlike charges attract. There is no possibility of repulsion for gravity or gravitational force. So if you have two such bodies, one maybe the Earth, the other maybe the Moon, for instance, and the distance between them, between their centers, of course, this is also important, not from the surface, from the center. So this force, there is a force of attraction. There is a force. Yeah, this is proportional to, let me see. And here, for example, in the electrical case, let's say we have 2 point charges. Let me call them Q1 and Q2. Q1 and Q2. And the distance between them, between the centers, but already they are like point charges, so there is no difference for the center over the surface. So this is also, this also creates a force between them. Maybe repulsive, maybe attractive, depending on the signs. So this also is proportional to some factors. What are those factors? For instance, this is the product of masses. That is the product of charges. This is inversely proportional to the square of the distance between their centers, r squared. Similarly, this is so r squared. But these are just proportionalities, so we should convert them into equalities. So to make them an equation, we have to put some constant here and some constant there to match the two sides as far as the units and dimensions are concerned. So this is, as we remember, of course we not go into the details of electrical cases now, but this is just a review of the similarity. For example, here the electrical force would be, of course, there is a term which is 1 over 4 pi epsilon 0, as we remember from other elementary electrical courses. And here, these are the charges, Q1 and Q2, if you have 2 point charges, divided by their distance squared. What do we have here? Similarly, yeah, we said product of the masses by the distance squared, and we need a certain proportionality constant here. That proportionality constant is the universal constant of gravitation. It is G, but capital G. So we should write a capital G here, which I will try to explain how it is found, and 1 and 2 by R squared. So these are quite similar equations. However, let me repeat that in the time of period of Newton and the foundations of gravitation, there was no electrical counterpart. So this force was totally absent. It wasn't known in those times, and only more than 1 century later, thanks to the works of some people like Coulomb, Ampere, Faraday, Lenz, and basically Maxwell, who collected them as a family of equations. Maxwell's equations, it was the name. So these parallelisms didn't help, for instance, Isaac Newton to work on the details of the gravitation. So basic idea was the following, as some written pieces tell us, written works tell us. For instance, Isaac Newton, Isaac Newton, 1642-1727, in around 1660s, for instance, was working on this idea. How was he working? For example, the very well-known anecdote says that upon the falling of an apple from a tree, he found out the gravitation, etc. There is no valid proof for this event, that the apple fell on his head, etc., and then he worked on this idea. However, Stokely was a biographer and one of his bosom friends who has written later about this. Yes, the apple is falling from the tree, and everything you leave by itself falls down. But is it correct that the force that pulls the apple from the tree downward towards the earth, is it possible that this force has the same origin as the force that keeps the moon in the orbit, for instance? This was the main idea, main concern of Newton. It is possible to find the value of gravitation, the value of the gravitational acceleration g, at the distance of the moon. Because, for instance, this is the Earth. So this is the Earth here. And here is the moon. Let me say, here is the moon. There is a force that pulls the moon downward towards the center of the Earth. That's why the moon is still turning around the Earth in a sort of circular way, in a fixed orbit, almost fixed orbit with a fixed, almost fixed radius. But here, for instance, there's a tree, and an apple is there. An apple is also falling down towards the center of the Earth. But what about the values of these accelerations? How can we compare them? Yeah, this is obvious. This is g, that we call little g now. Please don't confuse capital G with little g. This is the gravitational acceleration that we can consider as 9.8 meters per second square, although it changes from position to position on the Earth, as I will try to explain. but we generally, for instance, take it as 10 meters per second square. So it is a certain value on the Earth. What about the acceleration A on the Moon? Can we find it? Yes, we can, of course. Einstein also, Newton also did find the acceleration. How? For instance, the period of the Moon is easy to find. By simple measurements, you can find it, or even they could have found it in 17th century even. Alright, the period, from the period, for instance, it is 2 pi over omega, and also this force that keeps it in the orbit is the gravitational pull, but that's equal to, for instance, m, mass of the Moon. Let me say this is the mass of the Earth, capital M, mass of the Moon is little m, and v squared r, m omega squared r, r is the distance between the centers of the Earth and the Moon, m omega squared r is equal to the A Moon, so that A can be found. What is omega? Omega can be found from the previous equation, 2 pi over period. So if you put this squared here, acceleration at the position of, at the distance radius of the Moon turns out to be, after the basic elementary calculations, it turns out that A of the Moon divided by A on the apple, which is G now, G is the A at the distance apple from the center, is almost 1 over 3,600, almost. So this number, this ratio was found. On the other hand, it is also written that Newton thought about it as far as the radii are concerned. So what is the ratio of the radii, these distances? So for instance, if this is the Earth, it has a radius, let's say, capital R, and here is the Moon, and this distance is almost 60 R. So the ratio of the radii for the Moon and for the apple, which is just on the surface of the Earth, the apple is at a distance of 1 R from the center of the Earth. However, the Moon is at a distance of almost, remember the distance is 380,000 kilometers. However, the radius is 6,400 kilometers for the Earth. So it is almost a ratio of 1 to 60. However, if you take the square of this 1 over 60, you get 1 over 3,600. So it is equal to 1 over 60 squared. So it is now, it appears sort of that this force depends indeed on the radius squared, but inversely. The farther away the second object is from the first, the weaker will be the force of gravitation or attraction. But how can we have this capital G? If capital G, the gravitational, the constant of universal gravitation, if G can be found experimentally, of course, in that way, empirically. If G can be found by some clever means in 17th century, then several other things can be found in astrophysics, for instance. In astrophysics, of course, there is no astrophysics, the name astrophysics in those years in 17th century, but let's say celestial mechanics. Celestial means it is related with the things in in the sky, in free space. Celestial mechanics. So how can we find this G? This G was sort of calculated by a clever experiment carried out by Cavendish, Lord Cavendish, who is also an English astronomer. This G was found by an experiment as follows. For example, on a table, they place two spherical objects, two balls, for instance. This is a table, and let me say this is the line joining them. On a certain surface, a table, for instance, they put, or Lord Cavendish and his co-workers put two spheres, maybe at a distance of, I will get the value soon, two balls, for instance, here. And then, from above, two other little balls, let me show it like this, two balls were hanging by were connected by a light rod, very light rod, and the rod and leads to this dumbbell was suspended by a wire. For example, it is maybe like this. I can show a very elementary system, for instance. So this is the system which can rotate. It's like a torsional pendulum. So this is the wire carrying the dumbbell, but this dumbbell, of course, in a plane, it doesn't make up and down oscillations, but it can make oscillations around the vertical axis. But this wire that carries the dumbbell can be twisted. So if you leave the system alone, for instance, it can make oscillations around this z-axis. The idea is basically the following. First of all, the period of the dumbbell, this dumbbell, which is rotated this way, clockwise and counterclockwise from above, the period of the dumbbell can be found. And later on, by using this idea, one can find some other things. And indirectly, one can calculate this constant, and even further, one can conclude that the inner parts of the Earth consist of more massive, higher density matter than the crust, as we will see. There is one more detail here. Since it's a very small force, very weak force, it is quite difficult to detect the oscillations of this, the force of attraction. So, in the original version of the experiment, for instance, there was a sort of a mirror here, and some light was sent towards the mirror. So as this object is turning around the vertical axis, for instance, this is the torsional balance, and there's a mirror just at the intersection point of the wire and the rod, so that when you send some light towards the mirror, it is reflected on a certain scale. As this object turns very slightly, the reflected light sweeps a certain angle, so from this indirect information, one can get the necessary information to solve the equations. Now let's use some data to calculate this capital G. The mass of these spheres, let's say, let me call them capital M and capital M. These these dumbbells are little m and little m. This distance, length of the rod is, let's say, L is equal to half a meter, 0.5 meter. And the second, next information, the additional information was about the period. Yeah, of course, depending on the material you choose for this wire, vertical wire, as you twist the dumbbell, it takes a certain time to come back, and of course, it makes oscillations around the vertical axis to some extent, like a simple harmonic motion, and one can find the period. And we know how to relate the period to the frequency and the other things. This is a, by the way, this is a torsional, because there is torsion. It is twisted around a certain initial position. Torsional pendulum. So it executes simple harmonic motion vertically around the vertical axis. Then we have, for instance, T is equal to 2 pi root. Normally, if you have a mass spring system, it will be 2 pi over omega. For a mass spring system, as we have seen in the previous lectures, for a mass spring system which is oscillating up and down or back and forth, for a mass spring system, omega is root k over m. It's a linear oscillation, up and down or back and forth. However, here we don't have a linear oscillation. We instead have some angular oscillation. So that instead of k and m, we will have the corresponding counterparts. For instance, we don't have m, we have inertia I. For omega, in the new case, for omega we have, instead of m, we will have inertia I, rotational inertia, or moment of inertia. For this k, we don't have k, but we have kappa. Kappa is the counterpart, the corresponding quantity in the angular oscillation, simple harmonic motion. So here we have 2 pi, t is equal to 2 pi times inverse of this, so I over kappa. But what is I and what is kappa? I, so we don't consider these big balls. We consider the small balls attached to the ends of the light rod and hanging by a vertical wire which can rotate around the vertical axis. So that we have this ball, light rod, the other ball, and this wire that carries it. So this object has a mass m, this object has a mass m, and this distance is, let's say, b over 2. This is also b over 2. If you neglect the mass of the rod, which is a sort of error, but we do it for simplicity, they did also, Lord Cavendish also took into account only the inertia of the balls. So the inertia, remember, is m times b over 2 squared. But we have two such things, so we have to multiply by 2. Let me give the data for the masses. So mass of the big ball is 10 kilograms, which we didn't take into account yet. And mass of the little ball is 10 grams. 10 grams is 0.01 kilogram. So this is 1/1000th of the other. 10 grams, 10 kilograms. Alright? And the length of this, let me call it B. B is the full length. B is half a meter. So using these data, can we get I? Sure. I, therefore, turns out to be twice m b squared over 4. So these cancel. We have m times b squared over 2. So I, the inertia of this dumbbell, just the inertia of the little balls is mass, which is 0.01. B squared, which is 1/2, but square is 1/4. We have a 1/4 here and a 2 there, so it is 0.01 over 8. It turns out that, let me write I here, 0.0025, so it is 125, 1.25, 10 to the minus 3. So it is 0.0125, 10 to the minus 3. Okay. So this is the result for I. Of course, the unit is kilogram meter squared. So we have found I. We now should consider the value of kappa. Kappa is related with the K, the force constant of the spring. If we have again a mass spring system, we will consider F is equal to K times X. For a mass spring system, it will be F equals K times X. But now we have a rotational system, angular oscillations. For a mass spring system, so this is the object and it makes oscillations back and forth. So this formula was F equals K times X. There's a minus sign, but forget about it right now. But for a rotational system, that we have now, the dumbbell rotational system, instead of F we have torque, because remember in the rotational topics the force is replaced by the torque. So this is the torque. And X, which is the linear displacement, now becomes theta, the angular displacement, and the corresponding proportionality constant is just kappa. So this K becomes kappa. So this is the main idea. Something that creates the motion, either force or torque, and the resulting displacement, either linear or angular. And the proportionality constant in between is either K, force constant of the spring, or kappa, again, the rotational constant for the rotational pendulum, torsional pendulum. What about this torque and this theta? Now I will give some more information. It was again observed that theta, the angle theta, of course very small angle, because the system applies a very, very weak force, so that the change in the angle is very, very low. How much? The angle theta is found to be, angle theta means the maximum angle swept as a result of this force of attraction. The angle theta is found to be roughly 4 times 10 to the minus 3 radian. Remember, 1 radian corresponds to approximately 55 degrees. So it is 1,000th of it times 4. Very, very little angle, which is quite difficult to detect. However, by that clever means, sending some light and reflecting it by the mirror placed on the system, they can measure even small movements of this beam of light on the scale. Alright, so we have some more information. From tau equals kappa theta, we can write it. So we obtain this one, that one can be found now. What about this torque? This torque is the force that is applied on the little balls by the bigger balls, multiplied by the by the constant. So torque, now, since this is the system, we have the, let me show the top view. Top view is this. So we have these little balls, and maybe here the other balls. So this is hanging. If you look down the system from above, we have these little balls. Okay? If you look down, then you see the little balls, but very near those little balls there are the big balls. So this is the system. If you look down, this is, so the other balls placed very nearby, this will be attracted. But this attraction is balanced by the torsion of this twisted wire, so that there will be an equilibrium, and the small angle is written. What about the torque? The torque will be the force, this force, let me call it F, also this force, multiplied by this length, let's say B over 2 and B over 2. Well, what is the force now? Torque is equal to force times B over 2 multiplied by 2, because there are two forces that are acting and creating in the same torques in the same sense. So these 2's will also cancel. What about the force? That force will be capital G, which is unknown still. The purpose of this experiment is to find the universal constant of gravitation, capital G, multiplied by the capital M, the little m, divided by this distance squared, and let me now give the distance. It is almost 10 centimeters in the experiment. This, let me call it R is equal to 10 centimeters for each. So this is, let's say, R squared. This is the force, multiplied by this, that 2 is cancelled, multiplied by B. This has to be equal to kappa times theta. So on the left hand side, we have this full thing as our torque applied, and kappa is the coefficient of proportionality, and theta is the little angle swept. But we still didn't get this kappa. We can get this kappa from the period, because period, now let me also give the period, it is a very long period. For example, if you try to rotate this pendulum, torsional pendulum, around the equilibrium position, it takes several minutes to come back. So the period, let me write the period, it is around 770 seconds. The period T of oscillations is, let's say, T is equal to 770. So it's a very, very long time, more than 12 minutes. So the period is 770 seconds, nearly 12 minutes. So it takes almost 6 minutes to rotate to one side and 6 minutes back in the opposite sense. And from this information we can get kappa, because T, remember, is 2 pi root I over kappa, remember. Instead of M over K, we have I over kappa. I is obtained, T is measured, so kappa can be found from here. This T is 770. Let's take the square. It is equal to 4 pi squared I times kappa, and therefore kappa can be written as 4 pi squared I, which was 1.25 10 to the minus 3, as we have found a minute ago. And here we have 770, let's say 7.7 10 to the 2 squared, roughly, almost roughly we will have some approximation. So this kappa turns out to be 4 times pi squared is 10. 1.25 is there, 10 to the minus 3. If it were, for instance, 8 squared would be 64. Let's say it is around 60. 60 times 10 to the 4 is almost 6 times 10 to the 5. Almost 6 times 10 to the 5. So 4 times 125 is 5. So we have 5 over 6. 5 over 6 multiplied by some power of 10. What is that power? Plus 1. Minus 3, minus 5. So that it is almost, let's say, this is 4.8. So it is almost, kappa is approximately 8 times 10 to the minus 8. Approximately 8 times 10 to the minus 8. What is the unit? It is easy to get the unit, but let's say kilogram meter square per second square. So the number is almost this, 8 times 10 to the minus 8. Now we continue. So we have found the necessary pieces here. The only unknown is capital G, and we will find capital G from this expression directly. Now let's apply this expression. Capital G, which is the only thing unknown. Capital G multiplied by mass of the big object, which is 10 kilograms. Mass of the little one, which is 0.01 kilogram, 10 grams. Divided by distance between them, 10 centimeter, 0.1. So 0.1 meter squared, multiplied by the length of the rod, which is 50 centimeters, 0.5, equal to kappa, 8 times 10 to the minus 8, and angle theta, which is also 4 times 10 to the minus 3. So 10 to the minus 8, and the angle is 4 times 10 to the minus 3 radian. So it is easy to get G for me. Let's say the order of magnitude. G will be approximately, this is 32 divided by 0.5 multiplied by only the power of 10 minus 8 minus 3. This will be 0.01 10 to the minus 2 coming here, minus 2 divided by 0.1, so plus 1, so that this is approximately 6.4, so that G turns out to be 6.4 times 10 to the minus 11. As you see, this is 64. If you write it as 6.4, one other 10 comes here, so it is approximately. There are more exact values, as you know, 6.67 times 10 to the minus 11. What is the unit? On the left hand side, because remember F is equal to G, mass is M1 and M2 divided by R squared. So G has a unit of Newton meter square per kilogram square. So numerically it's a very, very small number. That's why we do not observe the gravitational effects, the pull of an object on the other object here on the Earth or in the classroom, for instance. For instance, if I put this pen here and the other pen there, according to this law of gravitation, every object tries to pull every other object. So that we should expect that these two pens attract each other and unite in a minute. However, we don't observe such unifications because there is a friction between them, between the surfaces and the objects, much greater than this little pull between them, the gravitational pull, so that we do not observe such effects on the Earth, for instance. For instance, this chair tries to pull the table, or vice versa. However, we don't see the table pull the chair or any other object nearby because of the other forces such as friction, which are much greater in magnitude than this little pull of gravity. However, when you come to free space, there is no friction, no other dissipative forces, no resistive forces between celestial bodies, the planets, the stars, etc. The only force that exists, the only interaction that exists in space is the gravitational force. Of course, later on, the interpretation changed a bit because, according to Einstein's general relativity, this effect that we observe, the pull between the objects in space or any other medium, occurs as a result of the effect of the body's masses around their vicinities. If there's an object here in space, for instance, and it has a mass, it sort of deforms the space around it, the nearby points. The greater the mass or the density, the greater will be the effect of this deformation. And as a result of this deformation, the objects that are maybe passing nearby are deflected and change direction. Even the photons, particles of light, particles of electromagnetic radiation are affected, influenced by this gravitational effect, so that they change the direction, although very little, but they do change their direction of their path because of the effect. For example, if here is the sun, for example, here is the sun, and let me draw it better. For instance, let's say here is the sun, and here is the earth, and over there, for instance, there is a star who sends light everywhere in each direction. So, for example, here is a certain star, but of course it sends the rays of light in each possible direction radially. For instance, this ray, this is coming and passing by the sun. However, the sun, having a certain mass, although not very huge mass in the astronomical scale, but with respect to our own scale, it is a considerable mass. The mass of the sun is 300,000 times the mass of the earth, by the way, so it is relatively important. So this ray, for instance, these rays which are passing nearby the sun are affected, so they change the direction a little bit, for instance. So this ray is coming, and after passing by the sun, let me draw the sun a bit closer. So this is deflected and follows, instead of this, follows a bit, I exaggerate very largely. So this is the earth. Therefore, there is a certain deflection in the ray of light coming from the faraway star. So we on the earth, for example, observe the apparent position of the star seems to be at a different position, because since we see this light, we assume that the star is somewhere here, which is wrong. But this causes, of course, there are much more massive objects, stars in space than our sun. So those neutron stars, for instance, the effect of those more massive objects is more pronounced, of course. So if there were a more massive object in the place of our sun, this deflection would be even more. And we would observe, in a wrong way, we would observe this star in a new position as if the star were there. So this is the kind of effect of gravitation. Now let's try to consider the formula that I have written here at the beginning. What was the formula? F is equal to capital G masses divided by r squared. Now let us try to derive. Now let us derive the equation, this force equation. The equation force is equal to capital G times the mass. Let me say capital M for one mass, little m for the other mass, and divided by r squared. Or let's use the other r squared. Let us try to derive this equation using some mathematics. Now let us try to derive the equation which is very widely known as gmm over r squared. But start with the spherical shell. Now let us take a spherical shell, not a full solid sphere, but a spherical shell. Of radius r, and calculate the gravitational force of this shell on an object of mass m at a distance r, capital R, from the center of the shell of mass m, at a distance capital R, just like this, capital R, at a distance r from the center of the shell. So basically, we talk about this situation. We have a, let's say it's a spherical shell. It's a spherical shell, so we have empty space inside. Assume this is a sphere, and here's a second object of mass m, where m is the mass of this shell, and this radius is, let's say, r, capital R. But capital R is the distance between the center of the shell and the little object at this distance, and little r is the radius of this shell. Now, first thing is to take a certain ring on this shell. Let me draw the picture again. So this is a shell. It has a certain thickness. So this is the thickness D. This is the center of the shell, and along this axis, here is the other object of mass m. But we consider some ring on this spherical shell. Let's say this is the, first of all, this is the remaining part. This remaining, and there's an empty space, as I said. And consider only some ring. Okay? So some ring. And this is the radius arc, which is fixed everywhere. And therefore, this angle also, let me call it theta. And this thickness of the ring is r d theta. Because r is the radius, d theta is that small angle. So this part is r times d theta. On the other hand, what about this vertical? That part is r sine theta. R sine theta. And remember also, as we have said here, the total distance from center to center is r. And only this part is r cos theta. So this part is r cosine theta. And we create a triangle. Also another triangle. It is not a right triangle. No angle is 90. For a certain ring, yeah, the angle may be 90, but we talk about the general, ordinary ring, so that the angle doesn't have to be 90 degrees. So it's not a right triangle. Any triangle, if you join this part with the little object, and of course the symmetric one here, it's just, by the way, it is like a ring like this, and this distance is x, that distance is x. And here we have the little object. Let me call this distance x and x. So consider only this ring and a little object, little mass element at the top and symmetrically down, diametrically down, the other one, the same mass element here. So what are the effects of these two opposite elements of the little object? So there is a force here, as you see. There is a force here, let me call it F1, and a force there, let's call it F2. And let's call this angle, angle phi. So this angle is theta, but the other angle is phi. Angle phi, angle phi. So first of all, let's take this ring and cut it open. If we cut the ring open, this ring of radius r sine theta, if we cut the ring of radius r sine theta open, what do we get? We get a strip. So this ring, circular part, is now cut open, so it is a rectangular strip. What are the dimensions? So this part is simply the circumference 2 pi r sine theta, and the thickness, as we said here, is r d theta. So it is r d theta is the thickness. Of course, it has also a thickness here. Since this is a three-dimensional object, it has a thickness T. This thickness T is valid for the strip as well. What about the volume? The volume of this ring is dV. How can we write this dV? It is the product of three things: the length, the width, and the thickness. The length is 2 pi r sine theta. The width is r d theta, and the thickness is just t. So let's unite them. dV now turns out to be 2 pi t r squared These are all constants. R is not a variable, R is a constant. This R is also a constant. Please keep in mind, the R's, little r and capital R are both constant. But what are changing? What are the variables? So we have here sine theta and d theta, because theta is changing. If you take this strip, it is maybe 15 degrees. If you consider this strip, theta is maybe 64 degrees. If you take this strip, theta is 11 degrees. So theta is changing. What else? X is also changing. X and theta are variables. But we should be, in order to get this integral, because by adding up all the contributions of these rings, because there are billions of rings on this shell. If you cut it, slice it into very thin elements, we have billions of rings having different radius and at this different distance from the little object. So x is a variable, theta is a variable. But in order to solve this integration, we should write one of them in terms of the others, so that we should have only one parameter, one variable. That will be x at the end. Now what about the mass of this strip? The mass of the strip is what? Ring is the strip. What is the mass? It is the mass dm. It is rho times dv. Rho is the general density, overall density. So that dm can be written, if you insert also rho here, it will be the dm. So we totally have 2 pi rho also t r squared altogether, some constants. We will call them some a, not to carry out through the calculation. But here the variables are sine theta and d theta. Next, let's write the force, net force on this little m. The net force on the little m is what? The net force on the little object m at the far away position is what? Here we see those forces. For instance, if you consider only a small element at the top and small element symmetrically down on the ring, then these are the forces they create. But if you consider the horizontal and vertical axes, F1 and F2, cancel each other in the vertical sense because they are opposite, but in the horizontal sense they are added. What is the added case? So the net force on M is, let me call it dF. It is capital G, sure. Mass of the ring, dm, multiplied by the mass of the little object m, divided by x squared, because this is the distance between them. However, we should introduce cosine phi, because we only have a net force along the horizontal axis. So cosine phi should be there. So there are some, let me write dm also, as we have found here. So df will be capital G, little m, multiplied by dm. What is dm? The whole thing. 2 pi rho t r squared sine theta d theta all divided by x squared multiplied by cosine phi. There are some constants. Yes, these gm, etc. So let me write them as a separate term. Gm times 2 pi times rho times t and r squared. The whole together. Let's call it A, for instance, and write it as A in the following calculations. And at the end we will replace. So A, a constant, all of them is called A. What are the variables next to that? We have a block sine theta d theta divided by x squared, and we have a cosine phi, because phi is also changing. There are three variables now, phi, theta, and x, which are changing accordingly. They are interrelated quantities, but we should get a way to relate them in terms of each other. That way comes from the law of cosines. By the help of law of cosines, remember that if you have any triangle, let me call these sizes A, B, C, for instance, and this angle, let's call it beta, for instance. If you have such a triangle, it doesn't have to be a right triangle. You can write, for instance, any side, let's say c squared is equal to a squared plus b squared minus 2ab, and cosine of this angle between a and b, cosine beta. This is a general law. It is called law of cosines. Let's check it for a right triangle. For instance, if this is the right triangle, then c squared would be a squared plus b squared, right, yes, minus 2ab cosine beta. But cosine beta would be b over a. Here we have b over a, so a's cancel, we have 2b squared minus 2b, therefore it will be a squared minus b squared as expected. So we check it. So it is correct for right triangles as well. But for any general triangle, we can write this law of cosine. We will apply it now to this triangle. I will keep the figure and then continue the calculations. Next, from this triangle, now we pass to the this triangle. X, just like this C, x squared turns out to be r squared plus the other r squared, which is the radius of the ring, which is our strip, r squared plus r squared minus 2r cosine theta. We can also write cosine phi because we need some three groups. So cosine phi is a group. We should replace x squared is another one, which will be our variable integration, so we can keep it. But sine theta d theta should also be replaced by some other thing which is related with the others, so that we can have only one variable of integration and carry out the integral, get the result. Alright, and from this triangle, cosine phi, for instance, can easily be written. From the triangle, cosine phi is just this side. What is that side? It is r minus r cos theta. R minus little r cosine theta divided by the hypotenuse x. So we have found an expression to put for cosine phi. So we will substitute this right hand side in the place of cosine phi. What about sine theta d theta part? It is again easy to get it because we can, let me call equation 1. By differentiating both sides of equation 1. By differentiating both sides of equation 1, what do we get? On the left we have only x squared. So if we differentiate, we get 2x dx. So we have 2x dx. R is a constant, no derivative. R is a constant, no derivative, minus twice the product by cosine theta. But cosine theta gives us minus sine theta d theta. So this minus becomes plus again. Now we obtain sine theta d theta to substitute here. Cancel the 2's. So sine theta d theta, this product is just x dx over r times r. So we obtained the auxiliary terms. For sine theta d theta, we will substitute this. For cosine phi, we will substitute the right hand side. What about r cos theta? And r cos theta can be found from equation 1. Let me write it again. Again from equation 1. Again from equation 1. If you keep r cos theta, it is r cosine theta, which we have to substitute there. R cos theta here. R cos theta from the previous equation is written as x squared. Let's take it the other side. So r squared, capital R squared plus little r squared minus x squared, all divided by the remaining part, which is 2r. So we will put this r cos theta here into this part. And then this we will substitute this cos phi in the previous equation, sine theta d theta in the previous equation, and we will only have one single variable of integration, which is x. And x will be integrated. So this df integrated through all the rings, all the possible rings of the shell, and we will get the final resultant force on the little m. So let's erase the unnecessary terms and keep the necessary. For instance, let's keep this term and erase the others. Now continue. We also have n is equal to integral df. This is the main idea. There are billions of such slices, different rings having different radii, but each of them has a certain contribution. If you add up all these contributions, you will get the total resultant force on the little m due to the spherical shell. So df, this is df by the way, it will be integrated. So inside the integral, what do we have? Let's keep it as a. At the end we can replace it. A integral. This term, sine theta d theta part divided by x squared multiplied by cosine phi. But as I said before, these two parts will be replaced by the corresponding terms on the right hand side. So that if let's take a outside. A is already out of the integral. Inside the integral, what do we have? Sine theta d theta. We don't write it, but we will write the right hand side. X dx over r. X dx over capital R little r. Divided by x squared. Let me write 1 over x squared. Multiplied by cosine phi, which is this thing. R minus, let me write first the first version. R minus r cos theta divided by x. So let's keep it and we keep it on the board. So this r cos theta on the other hand will be replaced by the last part here. So let me rewrite here. It is a. There is only maybe this cancels with that. Only that cancellation. Inside the integral we have dx divided by capital R little r x squared multiplied by r minus what? R cos theta. R cos theta is now replaced by the right hand side. So this is the last term. We have r squared plus r squared minus x squared all divided by 2r. Close it and close it. The rest is a simple integration of two terms. Now we continue with this from this line. So pass down. And if you play with the inside of the parentheses, we have a. Let me take r outside. They are constant. Inside we have dx over x squared multiplied by, now this becomes 2r squared minus, open up the second parenthesis, minus r squared minus little r squared plus x squared all divided by 2r. And this becomes only 1r squared. So we have, now continue here, a over, let's take this 2r also outside, 2 times r, r squared times r, capital R is squared but little r is 1, once, it appears there once. Inside we have the x over x squared multiplied by r squared minus r squared minus r squared plus x squared is the final form so far. Now what are the limits of this variable? Our variable is x. Our variable, only variable now, x, has limits. What is the nearest position? What is the greatest position? Farthest position? Here, the nearest position is x equals r minus r, and the greatest, longest position is r plus r. So x equals from r minus r to r plus r. So you will put these limits here. And then a over 2r squared r. Integral x equals r minus r to x equals r plus r. Well, what is the inside? Now we have two terms. Let's say we have two integrals. One is r squared minus r squared over x squared, the other with the dx of course, plus the other integral which is 1, only dx. So this becomes what? A over 2r squared r multiplied by, first term becomes r squared minus r squared multiplied by, since this becomes 1 over x squared turns out to be as minus 1 over x after the integration, minus 1 over x, limits between r minus r, r plus r, and next term is only x, again between r minus r, r plus r. So we will put at the end only part A. So let's keep A and erase the rest. Alright. So we continue. A over 2r squared r multiplied by r squared minus r squared, but times 1 over, let's take the minus sign here, 1 over r plus r minus 1 over r minus r, and after that we only have r plus r minus r minus r. But as you see from this subtraction, this is just, take it to the other side, r minus r plus r divided by r squared minus r squared. So this r squared minus r squared cancel. Those r's cancel. We have only minus 2r. But there's a minus sign here, so it becomes plus 2r. Here these r's also cancel. We have a plus 2r. So totally we have 4r. So totally, what do we have? F was the general term on the left hand side. A divided by 2r squared r multiplied by. From the first part, we only, and from the sum of them, we only have 4 little r. So these r's cancel, and let's substitute a here. So totally, F will be A. What is A? G, little m, 2 pi, rho, thickness t, r squared, divided by, there's a 2 here, another 2 after the cancellation.
right? There's 2 here, and here only we have an r squared. So we have 4 pi r squared, for instance. 2 times 2, 4 pi r squared. Let's group them. 4 pi little r squared, and what are the remaining terms? Capital G, little m, density, thickness, divided by r squared. But 4 pi r squared is the surface area of a sphere. If you multiply this by the thickness, you get the volume of the shell. Of course, inside it is empty, but just the thickness, because of the thickness of the shell, there is a volume. That volume is 4 pi r squared times the thickness. If you multiply this volume by the density, you get the mass, capital M. So we obtain, in fact, the final expression. So F is equal to capital M, G, capital M, little m by the distance r squared. What is r? R is the distance between their centers. It is the correct r, not the little r, correct r. Capital R. So we obtain this expression for a shell. Therefore, we understand that we can consider the shell as if it is concentrated at the center. So the comment, for instance, let me write an immediate comment. The mass m of a spherical shell can be considered as if it is concentrated at the center. Can be considered as if all the mass is concentrated, as if it is concentrated at its center. For instance, we have the shell. So there is material only here and a mass here. A second object of mass m. This is mass m. Now if you consider this, it is exactly equal to all the mass, capital M, concentrated at the center, and this m is there. So these two, let's say r is the distance between their centers. So that from this we see that it is as if all the mass is concentrated as a single point object at the center. So that we take this denominator as the distance between the centers of the object, not from the surfaces. And also, maybe we can also show that if little m, the second object, were somewhere inside the shell, not outside but inside. If we can also show that if m were somewhere, little m, this second object, if this little m were somewhere inside the spherical shell, what would be the force on it? Shell. The net force F on it would be 0. If it were inside, net force would be 0, because the limits of integration would be different. For instance, if instead of being here, the second object is somewhere here. And what are these values? Because now this is the value of x between these particles. So these are the rings that we have used, and x is the distance between those rings, etc. Then it is a good exercise to show that if the object is inside the shell, there is no force acting on it. But we have done this for a shell. But of course we have seen that for a shell it doesn't matter how exactly it is. So a solid sphere, filled solid sphere, can be considered as composed of billions of spherical shells, one after the other, without any empty space, for instance, between them. So that it doesn't matter whether it's a shell, spherical shell, whose inside is vacuum, or it's a solid filled material in a spherical shape, for instance, doesn't matter. So not only for spherical shells, but also for the solid spheres, this formula is valid, which was stated by Sir Isaac Newton in those years, in 1660s. Isaac Newton found out this relationship, also the how the force was acting, etc., in 1660s. But he published it only 20 years later, in 1687 or so, in Principia. As one of his friends tell us, for instance, Bertrand Russell, for instance, the English philosopher Bertrand Russell, says that Einstein was a shy person, not Einstein, Newton was a shy person, introspective person. So if, for instance, he had encountered the opposition by the, let's say, scientific community of those periods, just like Galileo did, he wouldn't publish a line, possibly. So it took him more than 20 years to publish, and it is the person was Halley, that we remember from the comet Halley. Halley was a friend of Newton who persuaded him to publish the Principia. So we have this equation dating back to the 1660s.